One night, the sky will stop looking familiar. A second galaxy will rise above the horizon, stretching across the darkness from one end to the other. Not a smudge, not a blur. Structure, spiral arms, billions of individual stars visible to the naked eye, draped across the night like a second Milky Way, brighter than the full moon. That galaxy already has a name: Andromeda, and it is already on its way. 2.5 million light-years away, moving toward us at 110 kilometers per second, locked on a trajectory that gravity set before our solar system formed. It will not stop. The approach has been confirmed. The trajectory is fixed. The outcome was decided billions of years before the first human ever looked up. So it's not a question of if it happens, but what happens when it does. Before you can understand what this collision does, you have to understand what is actually colliding. The Milky Way spans roughly 100,000 light-years across. 1 light-year alone is 9.5 trillion kilometers. The Milky Way is not one of those, not 10, not 1,000, 100,000. Andromeda is larger, 220,000 light-years in diameter, 2.1 quintillion kilometers, between 1 and 2 trillion stars. Our galaxy holds between 100 and 400 billion. Here is the comparison that makes the scale real. Shrink the Milky Way down to the size of a dinner plate on your table. Andromeda is another dinner plate sitting 2 meters away, already sliding toward the first one, already in motion, impossible to stop. In that model, our entire solar system, the Sun, Earth, every planet, every moon, every probe ever launched, is a single atom inside that plate, invisible to the naked eye, gone inside the disk. That is what is approaching. That is what is going to pass through us. But the word galaxy flattens something that exists in layers. The Milky Way is not solid. It is a rotating disk of stars, gas, dust, and dark matter spinning around a common center. Our Sun orbits the galactic center at roughly 828,000 kilometers per hour. At that velocity, it still takes 230 million years to complete one orbit. 1 galactic year. The last time our solar system was in this exact position in the galaxy, dinosaurs had not yet evolved. Earth was in the Triassic period, and the first small dinosaurs were only beginning to emerge. That is how long one orbit takes. And in the 13.6 billion years since the Big Bang, our galaxy has rotated roughly 60 times, 60 full rotations, while building everything we see in the night sky today. The Milky Way weighs approximately 1.5 trillion solar masses. Andromeda weighs roughly 2.5 trillion solar masses. Together, that is 4 trillion times the mass of the star that holds Earth in its orbit, all of it in motion, all of it about to interpenetrate in a process that will take billions of years to resolve. And almost everything you assume will happen when it arrives is wrong. The obvious assumption is this: 2 galaxies collide. Stars crash into each other. Everything burns. But correcting that assumption makes things worse, not better. Stars are not packed the way the night sky suggests. The nearest star to our Sun is 4.2 light-years away, 40 trillion kilometers. If the Sun were the size of a golf ball, that star would be another golf ball sitting 270 kilometers away. 2 golf balls. 270 kilometers of nothing between them. That is the density of a galaxy. So when Andromeda passes through the Milky Way, and it will pass through, not crash into it like a wall, the odds of any 2 individual stars making direct contact are almost zero. There will be some collisions. In a system of over 1 trillion stars, statistics guarantee it, but they will be rare. they will not be the mechanism of destruction. The mechanism of destruction is quieter. It is already operating on both galaxies right now. And the moment you understand what it actually is, the scale of what is coming becomes something different entirely. Think of it this way. If you randomly scattered 1 trillion golf balls across the entire United States, you could walk from coast to coast and probably never come within a mile of one. That is the spacing we are dealing with. Stars are not crowded. They are profoundly, almost impossibly isolated from one another. Even without direct impact, proximity alone changes everything. When two stars pass within 1 light year of each other, their gravitational fields interact. A planet that has orbited its star for 4 billion years suddenly feels a tug from a passing star. The tug is small, but orbits are balanced, not locked. Change the velocity even slightly, and the orbit shifts. To make it faster, the planet drifts outward into a colder orbit. Make it slower, it falls inward. The passing star moves on. The planet is left in a new orbit that may no longer be habitable. Multiply that across billions of stars, and the real mechanism emerges. No collision, disruption. Every stable planetary system that survives the initial pass is still vulnerable, because the galaxies will not collide once. They will collide, pass through each other, swing back under mutual gravity, and collide again and again. Each pass reshuffles the deck. Each pass gives gravity another chance to destabilize something that survived the previous encounter. The real force behind this event is gravity, and gravity does not wait for galaxies to touch. The gravitational fields of both systems are already reaching across the space between them, already pulling on each other's outermost stars. Objects in the outer edges of both galaxies are already being shifted out of orbits they have held for billions of years. The collision has already started. We are standing at the very beginning of it. As the two systems draw closer, that effect does not grow gradually. It compounds. Tidal forces begin stretching both galaxies from the inside. Entire spiral arms are pulled loose, flung outward into intergalactic space as long glowing rivers of displaced stars. Structures that took billions of years to form come apart in a fraction of that time. Our own spiral arm, the one our solar system has traveled inside for its entire existence, may not survive. It may be stripped away and scattered long before the two galactic cores ever meet. Every orbit near the boundary of both systems becomes temporary. Stable motion, the kind that has persisted for billions of years, stops being guaranteed. The tidal force grows with the inverse cube of distance. Cut the distance in half, and the force increases by a factor of 8. By the time Andromeda is 1 million light-years away, stars in our outer regions will already feel the pull. By 500,000 light-years, long streams of stars will stretch into intergalactic space. We have seen this in other mergers. The antennae galaxies have tidal tails stretching over 300,000 light-years. The tadpole galaxy has a tail over 280,000 light-years long, made of stars ripped from its disk by a smaller galaxy that passed through it. The Milky Way will look like that. 2 spirals bleeding stars into space, torn apart by each other's gravity even as they fall closer. Current simulations suggest a 12% chance our solar system will be ejected entirely during the merger, flung into intergalactic space by gravitational interactions. If that happens, the Milky Way becomes something we see from outside, a distant disk receding as our sun drifts alone through the void. The temperature would not change. The sun would still shine. The planets would still orbit. But we would be alone, in a way that no solar system in a galaxy ever is. And the disruption does not end with stars. Entire dwarf galaxies currently orbiting the Milky Way, satellite systems like the Large Magellanic Cloud and the Small Magellanic Cloud will be pulled into the chaos, their stars scattered and absorbed into the merger, their structures erased. But gravity does not stop at the stars. It reaches into everything between them. And what lives between them is what turns this merger into something that cannot be undone. The space between stars is not empty. It is filled with enormous clouds of gas, the raw material that stars are made of. And unlike stars, these clouds cannot pass through each other. When two of these clouds meet at 110 kilometers per second, they compress violently, and past a certain threshold, compressed gas does one thing. It collapses, it heats, it becomes stars. The rate of new star formation during a galactic merger can increase by a factor of 50, sometimes 100, over the normal rate. Thousands of new stars igniting across the merging system simultaneously. If there were a place to watch this from a safe distance, the combined galaxy would be blazing, a wave of creation running ahead of the structural collapse. The Milky Way contains roughly 10 billion solar masses of gas, vast clouds, some over 1 million billion kilometers across, cold and thin, temperatures dropping to negative 260 degrees Celsius. They exist in balance, waiting. When a gas cloud from the Milky Way meets one from Andromeda, they compress. Density spikes. The temperature rises. Pockets within the cloud collapse inward. When the core reaches 10 million degrees Celsius, hydrogen fusion ignites. Not one star, thousands, all from the same cloud, all clustering together in what astronomers call a starburst region. The antennae galaxies produce new stars at 50 solar masses per year. The Milky Way currently manages about 2 solar masses per year. The merger increased the rate by a factor of 25. The Milky Way-Andromeda collision could hit 10 to 20 solar masses per year, sustained for hundreds of millions of years. But the largest stars born in that wave live short, violent lives. They burn through everything they have in millions of years rather than billions. When they die, they go into supernovae, tearing the surrounding space with radiation and shock waves that compress more gas, ignite more stars, and feed the cycle further. A supernova releases more energy in seconds than our sun produces in 10 billion years. The shock wave tears outward at 36 million kilometers per hour, compressing gas, triggering more stars, which explode, which compress more gas. A feedback loop that does not stop until the fuel runs out. So, the merger does not destroy through impact. It destroys through compression, through ignition, through a chain reaction of creation and collapse happening across hundreds of thousands of light years at once. And drawing closer through all of it, feeding on all of it, are two objects that have been sitting at the center of each galaxy for billions of years. At the center of the Milky Way sits a supermassive black hole 4 million times the mass of our Sun. At the center of Andromeda sits another, between 100 and 140 million solar masses. Both are quiet for now, dormant. Neither is feeding aggressively, neither producing the violent jets of radiation that active galactic cores can generate. They are simply there, as they have been for billions of years. That will not last. As the galaxies merge, gravity will eventually pull these two objects toward each other. Not immediately, not in the first pass, possibly not for hundreds of millions of years after the initial merger begins. But once the process starts, it does not reverse. The black hole at the center of the Milky Way, Sagittarius, a star, has an event horizon roughly 12 million kilometers across, 17 times the diameter of the Sun. The entire star that gives us life could fit inside the event horizon with room to spare. Andromeda's black hole has an event horizon between 360 million and 480 million kilometers, larger than the orbit of Mars. You could fit the Sun, Mercury, Venus, Earth, and Mars inside it, and there would still be empty space left over. These objects are not stars. They are regions of space-time so warped by gravity that the normal rules of physics stop applying. Time itself runs slower near the event horizon. Light cannot escape, and anything that crosses the boundary is gone. During the merger, material begins falling inward, stars on decaying orbits, gas clouds stripped of angular momentum. All of it forms an accretion disk, a swirling maelstrom orbiting the black hole at speeds approaching the speed of light, heating to millions of degrees, glowing brighter than entire galaxies. This is an active galactic nucleus. When a supermassive black hole feeds, it does not just glow. The innermost disk emits X-rays and gamma rays. Magnetic fields accelerate particles to near light speed and fling them outward in jets extending millions of light years into space. Some of the brightest objects in the universe are black holes feeding this aggressively. As they spiral closer, every star near them is affected. Stable orbits stop existing. Stars are flung outward at velocities that carry them clear out of the merged galaxy. Others fall into decaying paths that end only one way. The two black holes spiral tighter. The gap between them shrinks from thousands of light years to hundreds to less. And as it does, they begin radiating gravitational waves, ripples in the fabric of space-time, on a scale that would make every event ever recorded by instruments on Earth seem like background noise. LIGO, the Laser Interferometer, Gravitational Wave Observatory, detects black hole mergers by measuring distortions in space-time on the order of 1/10,000th the width of a proton. The merger of two supermassive black holes would produce waves thousands of times stronger. Space-time itself would be ringing like a bell. And then they merge, one object, between 140 and 145 million solar masses, sitting at the center of what is no longer two galaxies, but one. The energy released in that final fraction of a second exceeds everything our Sun will produce across its entire 10 billion-year life. Roughly 5 to 7 million solar masses convert directly into gravitational wave energy. More energy than all the stars in the Milky Way will produce over the next billion years, released in less than 1 second. Permanent. Written into space-time as a record that cannot be undone. The question almost no one asks is what this means for a small rocky planet 26,000 light-years away that has been watching all of it without knowing. 4 billion years from now, when the first close pass begins, the Sun will be 9 billion years old. It will not be the star we know. By that point, it will have begun expanding into a red giant, its outer layers swelling outward. Its heat is increasing. The zone where liquid water can exist on a planet's surface will have already shifted far beyond where Earth currently orbits. Whatever exists here by then will already be living through a slow solar emergency that has nothing to do with Andromeda. The merger begins on top of a solar system already under terminal pressure, and yet our solar system will almost certainly survive the merger itself. The odds of another star passing close enough to disrupt our solar system during the collision are estimated at roughly 1 in a million. We are too small, too isolated. The same emptiness that makes the galaxy impossible to cross is what protects individual solar systems when two of them collide. But surviving is not the same as remaining unchanged. 4 billion years is not a number the brain can process. So compress the entire history of Earth, all 4.5 billion years, into a single 24-hour day. Humans do not appear until the last second before midnight. Modern civilization happens in the last tenth of a second. 4 billion years from now is an entire second 24-hour day from now. Everything changes in that span. Earth itself may not survive the Sun's expansion. Current models suggest the Sun's outer layers will reach past Mercury, past Venus, possibly past Earth. Even if our planet escapes consumption, the heat will vaporize the oceans, strip the atmosphere, and turn the surface molten. 4 billion years ago, Earth had no oxygen in its atmosphere, no plants, no animals, just single-celled bacteria. 4 billion years from now is the same distance ahead. Whatever exists then, if anything does, will be as unrecognizable to us as we would be to those ancient bacteria. And that assumes life survives at all. There is no guarantee. Evolution does not trend toward complexity. It trends toward whatever works. And what works in a world where the sun is slowly cooking the planet might be something that looks nothing like the biosphere we know. But let us assume something does survive, that something is still here when the merger begins. What would they see? The first sign would be subtle. The constellations would begin to shift, slowly at first, a degree every few million years, but accelerating. New stars would appear, faint at first, but growing brighter as the distance shrank. Stars from Andromeda, once too far to resolve, standing out as distinct points scattered across the sky. And then, roughly 3.85 billion years from now, Andromeda would become visible as more than a smudge. Its spiral structure would resolve. Individual clusters visible to the naked eye. By 3.75 billion years from now, it would be larger than the full moon. A glowing disk, bright enough to cast shadows. By 3.5 billion years from now, it would span 10 degrees across the sky, 20 times the width of the full moon. The organized spiral structure our solar system has orbited within for its entire existence will be gone. The Milky Way's arms, the galactic neighborhood that defined our position in the universe for billions of years, dissolved into something older and quieter. And the night sky above whatever remains on Earth will be unlike anything any human has ever looked at. Andromeda will stretch across it from horizon to horizon. Billions of stars, visible without a telescope, draped in a structure so dense and so vast that it dominates everything above. Stars from both galaxies scattered across new constellations that no civilization ever named. A sky so full it would have been unrecognizable to every astronomer who ever lived. The merged galaxy already has a name. Astronomers call it Milky, a single elliptical system. Older, quieter. Its violent starburst phase was long exhausted. The spiral arms that once defined both galaxies were replaced by a settled, irregular shape that holds the remnants of everything both systems ever contained. That is what the sky looks like when the collision is complete. But the species looking up at it will not be us. So here is what this actually is. A confirmed, locked, irreversible event that the universe committed to before the Earth existed. It begins with tidal distortion, arms stripped away, stars flung into the void between galaxies. Then, ignition. 100 times the normal rate of star formation, blazing across both systems as their gas clouds collide and collapse. Then, the slow spiral of two supermassive black holes, grinding closer across timescales that make the entire history of life on Earth look like an afternoon. Then silence. One galaxy. Old, settled, quiet, where two spirals used to turn. Our solar system will probably survive all of it. Too small to be a target, too isolated to be destroyed. A single atom inside a plate, drifting through the chaos without ever being touched by it. But the civilization that discovered the collision, that measured the approach velocity, that named the merged galaxy before the merger had even begun, will almost certainly be gone long before any of this becomes visible in the sky. The problem was never the distance. It was what 4 billion years does to the question of who is left to watch. By the time Andromeda fills the sky, the species that saw it coming will already be a memory the universe never kept. The merger is already in motion. It will determine whether anything is here to witness it or not. And the universe will not slow down to check.